Let's now give a formal definition of the instantaneous rate of change. Recall that we just found if s of t is position and v of t is velocity. Our velocity v of t is the instantaneous rate of change of position. We just found that at time t equals a, the velocity v at a is the limit as delta t goes to 0 of s of a plus delta t minus s of a all over delta t. In other words, we're calculating our change in position divided by the change in time over a smaller and smaller time interval until that time interval becomes nearly 0. Let's use this to define the instantaneous rate of change for any function. In general, the instantaneous rate of change of a function f of x at x equals a is given by the limit as delta x goes to 0 of f of a plus delta x minus f of a all over delta x. Again, we can think of this as our change in our function f on top all over our change in x, delta x, where the length of our interval, delta x, gets smaller and smaller and smaller. This instantaneous rate of change of f of x that we just defined is called the derivative of f of x at x equals a, and we write it as f prime of a. So we now have our derivative. F prime of a equals the limit as delta x goes to 0 of f of a plus delta x minus f of a all over delta x. The rest of our studies for this semester will be on this derivative, so this is a very important definition. Let's use our definition to compute an example. Say we're working with the function f of x equals x squared. Let's find the derivative f prime of 1. In the corner, we have the graph of x squared, which will help us visualize what we're computing. Here, we're using that a equals 1. So f of 1 equals 1 squared, which is 1. This gives the point 1, 1. To compute f prime of 1, let's start by approximating it using different values of delta x. For whatever value of delta x we use, we get that f prime of 1 is approximately f of 1 plus delta x minus f of 1 all over delta x. Using our function f of x equals x squared, f of 1 plus delta x is 1 plus delta x squared, and f of 1 is simply 1. As we did before, let's approximate this for smaller and smaller values of delta x to help us figure out what f prime of 1 is. As we did before, let's approximate f prime of 1 for smaller and smaller values of delta x until we have a guess of what f prime of 1 really is. Let's start with delta x equals 1. Then f prime of 1 plus delta x is 1 plus 1 squared, which is 4. That gives the point on our graph 2, 4. And f prime of 1 is approximately f of 1 plus delta x minus f of 1 all over delta x, which is 4 minus 1 over 1, or 3. So our first approximation of f prime of 1 is 3. And graphically, we can think of this as the slope of the line between the points 1, 1 and 2, 4. Let's carry on with delta x equals 0.5. Here, f of 1 plus delta x is 1 plus 0.5 squared, which is 2.25. So we get the point on the graph 1.5, 2.25. Now computing our approximation, f of 1 is roughly f of 1 plus delta x minus f of 1 over delta x, which in this case is 2.25 minus 1 over 0.5, which reduces to 2.5. So our new approximation of f prime of 1 is 2.5. Again, we can visualize this on the graph as the slope between these 2 points. Continuing with delta x equals 0.1, we get that f of 1 plus delta x is 1 plus 0.1 squared, which is 1.21, which gives the point 1.1, 1.21. Approximating f prime of 1 here, as we did before, we get 1.21 minus 1 over 0.1, which is 2.1. So our approximation for f prime of 1 now is 2.1. And we can visualize this approximation as the slope of the line between our 2 points. Shrinking delta x even more to 0.001, we get that f of 1 plus delta x is 1 plus 0.001 squared, which is 1.002001, which gives a point incredibly close to our first point. Doing our calculation as we did before, we approximate f prime of 1 to be 4 minus 1 approximating f prime of 1 as we did before, we get that it is roughly 1.002001 minus 1 all over 0.001, which is 2.001. So our approximation to f prime of 1 is now 2.001. Again, we can visualize this as the slope of the line between these 2 points. Let's do one more approximation with delta x equal to 0.00001. F of 1 plus delta x is, let's approximate f prime of 1 one more time using delta x equals 0.00001. Here, f of 1 plus delta x is 1 plus 0.00001 squared, which is 1.000020001. Calculating our approximation for f prime of 1, again as we did before, comes out to 2.00001. So our last approximation for f prime of 1 is 2.00001. And again, we can visualize this approximation as the slope of the line between the 2 points, even though the 2 points are pretty much on top of each other right now. Let's consider now what happens as delta x goes to 0, because we know f prime of 1 equals the limit as delta x goes to 0 of f of 1 plus delta x minus f of 1 all over delta x. Using the approximations we just calculated, it appears as though this is going to 2. So our best guess at this point is that f prime of 1 equals 2. Let's consider our last example, paying more attention to our graph. We are trying to approximate the derivative at x equals 1, or in other words, at the point 1, 1. To do this, we had to pick a second point near our first point and calculate the slope of the line between the 2 points. To make our approximation better, we chose a different second point, even closer to the first one, and calculated the slope of the line between those 2 points. By taking the limit as delta x goes to 0, we mean that we are picking our second point closer and closer to our first point, and then calculating the slope of the line between those 2 points. To get a better and better approximation, we had to take a closer and closer point and calculate the slope of the line between them. In our last calculation, our second point was so close to our first point that we would have to zoom in a lot to tell that it was even different. But algebraically, we could still compute the slope of the line between those 2 points. The conceptual idea of what happens as delta x actually goes to 0 is that those 2 points become 1. That original point, 1, 1. And the derivative is the slope of this line that only touches our graph at the 1 point. Here it's 1, 1. So we can think of the derivative f prime of 1 in our original definition, the rate of change of f of x at x equals a. But graphically, we can think of it as the slope of the line tangent to f of x at x equals a. Another way to interpret this is that it's the slope of the curve at x equals a. We will use these different interpretations of the derivative throughout the rest of the course.